Hello, and this is our Unit 9 for Physical Geology. It's going to be on earthquakes, and basically an earthquake is a rapid release of stored energy, potential energy that's built up by tectonic forces, and it either breaks the ground due to compressional, tensional, or shearing forces, and those create the three basic types of earthquakes. They produce what are called body waves, which we'll learn later are primary or secondary, first or secondary waves, which move through the body of the Earth, and then we also have some waves that move across the surface, and we'll talk about those as well. But basically what I did is I showed this image of obviously not the way this building was planned, where it actually actually crushed the concrete. You can see the rebar in there causing all kinds of problems. This is a European picture because of that speed sign. And we talked about building up pressure, where we actually had built up of potential energy and then a rapid release of kinetic energy, and then going back to square one. Tsunamis in Japan, and then this is supposed to be working, but apparently doesn't. But this is a shearing force, side-to-side force, where the other side, which seems to be moving to the right, make this a right lateral fault. And then this is the 1906 San Francisco earthquake. Actually was a very large earthquake. Most of the information, or most of the damage, was caused not by the actual earthquake, but by the breaking of electric lines, which were newly installed, and gas lines, which filled up the wooden buildings. And when the sparks actually started to fly, buildings burst into flame, catching the rest of the block on, and it happened enough where we actually had some very dire damage to San Francisco, again back in 1906. Earthquakes are a vibration of the earth produced by rapid release of energy, massive release of energy, much stronger than what we normally think of in terms of bombs, and sometimes even more than volcanic eruptions. Earthquakes occur along plate boundaries, weak places of weakness, weakest links, which we now call the fault, and the potential energy builds up, produces the stress, until the rock finally can't hold it anymore, and it's a rapid release of kinetic energy which produces seismic waves, which actually is the earthquake. Earthquakes radiate energy from all directions. It's like throwing a rock into a pond. You can hear the rock hit the water, so it goes through the air up at you. You can see it moving horizontally across the water, but if you were actually in the water, you'd hear it, so it goes down. So it not only goes vertically, it also goes horizontally. This is an earthquake caused by compression, where one plate is being pushed in towards the other. It's going to make what's called a reverse fault. And we actually have a fault line going across, or the scarp going across the surface. We have the actual fault, and we have the point where the earthquake happens, which is called the focus. Focus is the place beneath the earth where the rock actually breaks. It's showing you the weakest link. It produces the seismic waves that radiate out in all directions, X, Y, and Z. The focus of an earthquake is the underground part. It's also called the hypocenter. And then there's the point directly above the earth, which is called the epicenter. This is normally when you hear the earthquake, they talk about it being 30 miles outside of Los Angeles. That's the point directly on the map that you would see, although the focus may be miles or kilometers, many kilometers underneath the surface of the earth. Stress and strain on the rock. We can have them by, well, actually let me just do it this way. Crust is made of solid rigid plates. These move cause distress, strain, and tension, which bends the plates. We talked about metamorphic rock before, and then we're also talking about this rock. This is a normal fault. This is caused by tension, where this plate is being pulled apart from this plate and causing a slide down. Stress is too strong, the plates will bend, and then eventually they'll break, crack along the fault, and this is what causes the earthquake. Stress and strain. We have three different types of strain built up in rock, and it actually is caused by stress or deformation. We have what's called elastic, and this is when the stress is actually created on the rock. It stretches or compresses the rock, but once we release the pressure, the rock goes right back to its original starting point. We have plastic deformation, where we actually do the same thing. We stretch the rock, and then when we release the pressure, the rock stays the same shape because it's more like a piece of plastic. And then we have what's called rupture, maybe we're talking about the Bible. Rupture, where we actually put the force into the rock and the rock actually gets to the point where it breaks, and when we release the energy, it's the actual breaking of the rock which is going to cause the earthquake. This is not earthquake causing, this is not earthquake causing. Brittle material cause elastic, actually brittle materials break during the elastic deformation, so when we actually have something that's very strong, very brittle, sort of like peanut brittle, when you actually put this elastic stress on it, it will settle back into its original size and shape, except it'll be broken. Forces of an earthquake. Tectonic forces apply stress to the rock in three basic forms. We have what's called compression, where we take the opposite sides and push them together. We have what's called tension or expression, where we actually take the extension, where we take the rock and we pull them in opposite directions but away from each other. And then we have what's called shearing or transform, which we push in opposite directions, but we do them on the side, where we just literally, it's like a pair of scissors or a pair of shears. It literally rips the rock apart. Tensional stress, pulling it apart. Compressional stress, pushing it together. And shearing force, actually going opposite directions side by side, opposite directions away, opposite directions toward. Same things. Here's the San Francisco earthquake, again, 1906, where we actually had a shearing force. And love these Yammer things, where we actually had shearing forces, where we had one plate move one way and another plate go the other direction. I'm not sure exactly what direction this is looking, but this would be called a right lateral or strike slip fault, because the plate on the opposite sides goes to the right. If you were standing over here, you'd see this one go to the right, so it doesn't matter. So you're building up stress, you got potential energy. The kinetic energy is gone, it's the earthquake, and you can see this fault moved off to the right also, so this is still a right lateral fault. Elastic rebound, what we're going to do is we're going to build up some pressure in this rock, and you can see we're building it up, and if I stop right there, you can see this is actually moving now to the left, so this will be a left lateral fault that is shearing because the opposite directions are going side by side. They're not going toward each other, away from each other. You're actually shearing it like a pair of shears. Builds up the stress, and then finally can't hold it anymore, releases the energy as seismic waves, and that was the earthquake. And there's where the rock breaks, and you can see it actually releasing all the stress. Lines go back to straight the way they started, and if those are survey lines, you can actually measure the distance, how far they've moved. If it was a road, a river, anything along the surface, you can measure the distance, and this is a left lateral fault because it moved to the left. Stress and strain along faults. When we get to plate tectonics, which is the next unit, we'll talk about colliding plates, we'll talk about ripping apart plates, and we'll actually talk about shearing boundaries. But we have compressional forces, we have tensional forces, and we have shearing, which produce transform boundaries, divergent boundaries, or convergent boundaries. Okay, stress and strain, energy released. When stress of certain parts of the plates exceed the threshold sustaining the elasticity, the thing that actually holds it in place, the plates will rupture. And this release is called the earthquake, releasing seismic waves. The energy is transmitted through the plate as seismic waves. It also produces heat. It also produces sound. The amount of energy released will be determined by the strength or magnitude of the earthquake. So bigger seismic waves, more heat, more sound with bigger earthquakes, and smaller ones, smaller amounts of these with smaller earthquakes. Fault origin. We're going to talk about a couple of different parts of anatomy of a fault. And we have what's called the fault plane. The fault plane is the actual fault itself, and that line that goes inside the earth, we only see the top part up here. We have the fault trace. The fault trace is going to be this location where it would be raised or lowered, or it would be moved side to side. And then we have what's called the hanging wall. If you were standing right there, this would be the wall that's above your head, and this would be the wall that's below, and that would be called the footwall. The fault plane is where the action actually happens. It's along this location right there, and that's the earthquake. The flat surface may be vertical or sloping, could be straight up and down in case of a strike slip fault, or it's going to be angled in terms of a reverse or a normal fault, which we'll talk about later on. And then we actually have what's called the fault trace, and that's the mark along the surface that actually is going to show the release of that energy. Origins of the earthquake. A lot of times when these faults were on the surface, miners who wanted to get in for gold or diamonds, whatever, would actually just enlarge that crack and go in. So the terminology of the hanging wall, the wall that was above their head, or the foot wall, they also had a right and a left wall, but we don't really talk about that with earthquakes. We do talk about the hanging wall, the one above the head or the one above the fault, and the foot wall, the one below the feet, or the one that's actually below that plane. When the fault actually breaks, it creates a hanging wall and a foot wall. When the fault plane is vertical, there's no hanging wall. If it's straight up and down, there's no hanging wall or foot wall in the case of a strike slip fault. Three basic types of faults, and this is where I'm going to call this video an end. We have what's called the normal fault, and that's caused by tensional or extensional force, where we actually take the two plates and we pull them apart, opposite directions, stress and strain, and what happens is that the hanging wall slides down, and this is what's called a normal motion. If you think about this hanging wall like a ball, it'd be normal for it to fall along this hill, roll down. If you take a look at the age of the rock, we have younger rock actually next to older rock. So younger rock is on top of the fault and older rock would be below. So if you take a look at that yellow right there, this is a lot younger than here. This yellow rock should be up at this surface, but it's actually slid all the way down. And then you have erosional forces. That scarp actually does get eroded, and it's tough to actually see the fault anymore. The fault gets filled in with sediment. The next earthquake happens, and it could be a surprise. We have what's called a reverse fault, and this is when we take those opposite stresses, we push them toward each other. It's caused by compressional forces. And when you take a look at the rock on this one, we actually have older rock on top of younger rock. So there's the young rock at the surface, here's the young rock at the surface, and you can see there's new rock forming as the water washes down, puts sediment on top of it, but we actually have younger rock sitting on top of older rock in terms of that fault. And then we have the last type, which is called a strike slip or a lateral fault, caused by shearing, opposite forces going side by side, and we can actually change the course of rivers, roads. You can actually see the orchard here, and I've got to assume that these two trees used to be in line, so that one looks like that's a left lateral fault. With left lateral if the things move to the left, and right lateral if they go to the right, and just independent of the direction that you're on, you could flip these around and you still see it go to the left, or flip these around, it still goes to the right. And this happens along strike slip. They're not up and down motion, but it's actually a side to side motion. These faults are usually vertical, so we don't have a hanging wall or a foot wall. I'm going to just click the next one, but I think actually we'll talk about this one too. Reverse fault, normal fault, push them together, opposite directions toward each other, pull them apart, opposite directions away from each other, and actually opposite directions side by side. The reverse is caused by compression, normal is caused by divergence or tension, and we have this one by lateral or transform faults. And again, compression, where we actually get the hanging wall, which would be this side, sliding up, that's reverse. We do this one where we actually get the hanging wall, and I'll show you this in a better version, but basically what happens is the inside drops down, producing hanging wall moving down for a normal fault. And then we, along these mid-ocean ridges, where we get the ridge offset, we do get what's called the side-to-side motion. This is what's going on in California. That's the San Andreas Fault. Sometimes these are under land masses. I might as well show you this one too. And I can't get this one installed into the PowerPoint, so we're going to have to use the website. Normal fault, if you take a look at this one, hanging wall, foot wall, normal fault, we're actually pulling these away from each other, and you can see the hanging wall slides down and then erodes to a flat surface, but we get new rock sitting on top of much older rock. For a reverse fault, we actually push together, and now we're getting younger rock on top of older rock. And strike slip, where we can actually get the shearing forces and slip them beside. Okay, that'll work. Thanks for stopping by.